Jason Roselle is a supervisor for the Wisconsin Department of Transportation Southeast Region. Since 2011, he has been overseeing the construction of the Southeast mega major programs, including the Mitchell Interchange, the Hone Bridge, the Zoo Interchange, the Wisconsin Valley Development Roads. He has 20 plus years of industry experience. Jason is a graduate of UW-Platteville and is a registered professional engineer in the state of Wisconsin. Joining him today, also from the Wisconsin Department of Transportation, is Sean Race. Sean is a project manager in the Southeast region. Since 2012, he has managed multiple projects in the Southeast Mega Majors program, including the Zoo Interchange and the Wisconsin Valley Development Roads. He has 15 plus years of industry experience and is a graduate of University of Wisconsin-Milwaukee and a registered professional engineer in the state of Wisconsin. We are recording this presentation. I'll let everyone know. So I will have my camera off, and please everyone, if you have questions, use the chat feature on the Zoom at the bottom. If you turn your camera on, you're just going to get recorded and put on our YouTube page, which you can find also linked to on our website. Check us out. We've got tens of dozens of subscribers and great videos from all of our last year's content. Anyway, I will turn it over to Jason. Thank you again for being with us today.
Yeah, good morning, everyone. Thank you, Chris. Good to connect with you as well. As Chris stated, I'm Jason Roselle, construction supervisor for Southeast Freeways for the DOT. And yeah, excited for the opportunity to share a little information with your society here about the Zoo Interchange project and some of the geotechnical considerations that were considered and worked on throughout the design and construction. So there we go. Just a little bit about the project. So it's in the Milwaukee area, southeast part of the state. The hub of the traffic kind of coming up from Chicago, heading to Madison, heading up to Green Bay. It's the busiest interchange in the state of Wisconsin with almost 350,000 vehicles that travel through it every day. It's named the Zoo Interchange because it's adjacent to the Milwaukee County Zoo, which if you haven't been to is one of the best zoos in the country. So this project is a long time in the making. It started back in 2007 and construction started in 2013. And so there's been design and construction going on this project for almost 15 years now. And it's a $1.5 billion project, $830 million in construction value. This is the third mega interchange project for the state of Wisconsin. First mega was the Marquette Interchange, which was back in the early 2000s, mid 2000s. Then we moved on and reconstructed the Mitchell Interchange down by the Mitchell International Airport, and now the Zoo Interchange. So a unique aspect of this project is that it was the first fully integrated 3D model project for the state of Wisconsin. So we used that in various ways, and Sean's going to showcase a little bit of how we used it with some geotechnical stuff. We did complete the core of the interchange back in 2018, and all that's remaining is just the north leg of the zoo. So there was some funding issues there that pushed that leg of the zoo into the current time frame. So here's just a little bit of an overview again of like kind of the overall project, the various contracts and lettings that occurred over the last decade here. Like I stated, we started in 2013 and substantially complete in 2018 with various contracts kind of staged for efficiencies throughout the corridor. And, we built kind of some of the adjacent arterials so that we had those rehabbed and reconstructed for diversion of traffic during the construction of the actual core. We maintained 2 lanes of traffic throughout the project in the core and all the cardinal directions. We did have long-term ramp closures, system ramps during the project, but in the cardinal directions, we maintain 2 lanes of traffic at all times, except for when we're doing night work. Just some stats on the project. So, 50 PSC deliverables. So a number of contracts, as I stated, to kind of deliver this overall program. A number of real estate acquisitions, and kind of what we call a mega project within the mega project. We had over $100 million of compensable utilities. The majority of that being American transmission lines that had to be relocated throughout the corridor to allow for the construction. So a big effort there to get utilities figured out for this project. And then two major impacts with the Union Pacific Railroad. We had a tunnel extension and a reconstruction of a bridge back in 2014. And then we have a bridge that's being reconstructed as we speak that Sean's going to touch on just a little bit. You can see some of the numbers there with the number of structures, retaining walls, noise barriers, sign structures, and just the entire interchange is reinforced concrete pavement. So you can see the numbers there on the cubic yards of concrete. And then just a quick before and after picture for you. This is looking at the old interchange, a picture from 2008. And, kind of an old, outdated design. It was built in the 1960s, like a lot of our interstate system. And, it had the left-hand exits, had kind of that football in the middle there with the ramps. And the new interchange was designed with, full federal standards. Everything's right-hand exits. And now it's flyover ramps instead of this one was a little bit more at grade. So just a picture here from 2018 of what the new interchange looks like. And you can see quite a drastic change to the landscape here in this area. And, just the complex staging that was required to build this while maintaining 2 lanes of traffic. With that, I'm going to turn it over to Sean, and Sean's going to now walk through some of our geotechnical considerations for the project.
All right, thanks, Jason. Good morning, everybody. Appreciate the time to speak to you guys today. Obviously, Jason went through it, and it was a massive project, but the goal with this presentation today, we're going to talk about some geotech considerations and specifically some challenges we had that hopefully you guys all find interesting, and this kind of outlines everything I'm going to cover. Obviously, we have limited time, so I can't spend too much time on each one, but I'll do my best, and then once we're done, hopefully we got a little bit of time for questions before the next presentation. So starting on with foundations, the predominantly foundation type we used on the interchange was driven piles, both H piles and steel cans. But for our flyover structures, we actually had 5 of them. Just given the spans and the loading required, we knew they were going to have to use drilled shafts. Some of these were obviously chosen due to the loading, but also because of the room available to construct the foundations. This picture right here is, on our end, we call it core 1, core 2. We had a whole bunch of lets for this project, but the 2 main projects that built the core of the interchange was core 1, core 2. This project is taken kind of at the completion of core 1 before the start of core 2. So obviously you can see there's some new infrastructure, but there's also some existing. And obviously the challenge with all these projects is to keep lanes open for traffic. So we had limited space available. So we knew we were going to have to use drilled shafts. So prior to construction, I think this was in 2010, 2011, we did a load test program. We actually went out and drilled some shafts in the core of the interchange. The primary purpose, we wanted to compare capacities and settlement of the shafts both with and without base grouting. Base grouting, basically, we inject high pressure grout at the base of the shaft to improve integrity. We actually precast tubes in the shaft as a concrete's poured. So we ran this load test program, and the results definitely verified that the use of base grouting improved both capacities and substantially decreased settlement. So it definitely allowed us to optimize the design. So drilled shaft construction, we had some big shafts on this project. They were up to 10 foot in diameter. One of the tricks was to schedule the staging to allow construction, because even as a drilled shaft, the actual footprint of the shaft would be less than a big pile group to support some of these piers. You still have to get the crane and everything in there. So some of the staging on one of our bridges in particular, the east to south bridge, we called it, the shafts actually for some of the piers were drilled in May of 2016, but the bridge didn't open till winter, almost Thanksgiving of 2017. So those shafts were drilled. We staged traffic around it, and then they really just sat for over a year into the next construction season until the piers were poured. So that was one of the considerations. Some lessons learned that we took from previous mega programs was, obviously with these bigger shafts, you can see on the picture to the right that steel rebar cage is huge, and just the lifting of that, the installation, there's a lot of room for error and issues that can resolve. So we developed for every bridge, there was a trial drilled shaft program that actually in contract, they had to go out and essentially do a trial drilled shaft to prove that, their means and methods would work out. And it was actually very beneficial because we found out, especially with some of these shafts, that the contractor did have some issues and they were able to correct them. And, we avoided things as actual production shafts ensued. Some other lessons learned from previous projects, we did segmental full depth casing for all the shafts as well as the wet method, because in this area and some of the other megas that we did around the area, we had water table concerns and granular layers, and we had intrusions into our concrete that we want to avoid. So the full depth casing with the wet method, and then we also did CSL testing to verify the integrity after shaft construction, allowed us to have a really good superior product out there. Retaining walls. So as Jason mentioned on one of the previous slides, we had, with the enormity of this project, we had a lot of retaining walls. We had over 100 in the program. Our predominant retaining wall that we would always utilize, based on conditions, would be a standard MSC wall with sand backfill. We had some areas where there were significant cut walls. We would move on to soldier pile with tiebacks depending on the height of the wall. And then in some instances, we also had secant pile walls, specifically if we had a wall needed at a bridge abutment where the retain height was so high and it just made sense to use a secant wall to support the abutment and retain the slope. And then we had some other unique instances where Jason mentioned that, there was $100 million of utility locates, but we had a large transmission lines through the project that some of the lines could not be relocated, until partway through the project. So we actually had some areas where it may have been an MSC wall or a soldier pile with tieback wall, but we actually went with a secant wall because we had to support the embankment that was holding up the existing tower before that could be removed. And then we also had an instance where we had a hybrid wall that had to be considered with the design because the wall height got kind of high. It was a cut wall. So the majority of the wall was soldier pile with tiebacks, but there was an apartment complex with a swimming pool adjacent to the wall, and there was some major concerns with deflection and any impacts to that pool. So we actually had a hybrid wall where we had soldier pile and lagging with tiebacks, and then we had secants in between. One other I was going to hit real quick that the other unique wall, the MSC Piano Wall, we call it, because if you kind of look at it, it looks like a piano with the parapet on top. And all this allowed us to do was allow for more rapid construction because the coping and parapet's already precast with the wall. So in areas where the retain height wasn't really high and we knew that the construction timeline was critical, we went to this kind of wall and it had quite a bit of success with it. All right, earthwork and grading. I was mentioning walls before. We had an area in the southeast quadrant of the interchange where southwest quadrant interchange, but two of the flyover ramps actually landed down there. So it was really an intricate area. We had 4 retaining walls kind of essentially built up upon each other, but doing initial borings, we had a compressible layer between 20 and 35 feet below ground surface. During the geotechnical analyzing process, that it was looking at if, we did standard construction using sand backfill with these walls, we'd be talking upwards of a foot or more of settlement. So then during design, they looked at some options. One would be to EBS this entire area, which the volume of earth to remove was massive, and then also the backfill. And we settled on using lightweight foam concrete fill in lieu of the EBS to save a substantial amount of dollars. I think the estimate was approximately $10 million that was saved by not going with standard EBS. One of the unique things with lightweight foam concrete fill, the entire mass is basically made up of just cement. So if you envision it, it's essentially an 8 to 9 bag cement mix, but there's no aggregate or sand, and it's basically just foamed up. It's they call it foam. It's essentially dish soap type material. But that decreases the unit weight from, standard sand would be 120 pounds per cubic foot. With this lightweight foam fill, we're at 30 to 35 pounds a cubic foot. So it's almost 25% of the, your standard sand weight, which is a substantial reduction. One of the challenges or issues we found with this material is that the high cement content, you just got to be careful what you do with any byproducts, because, untreated or latent cement mixed with other materials can lead to other issues. But that was one of the challenges. But yeah, we were able to use this material successfully to avoid the large amount of EBS. Trenchless excavation. Obviously on a project this size, we had multiple storm sewer, sanitary sewer, water main, both crossings of existing freeway, which obviously we had to keep open. That picture on the left kind of illustrates, I think this is a sanitary board. They had to go under the road, but we also utilized this for any sewers or predominantly storm sewers where we knew the excavation was greater than 30 foot in depth. It was definitely more cost effective to go this route, and just with the less disturbance and concerns with disturbing adjacent soils. So we had quite a bit of trenchless excavation, predominantly jack and bore and tunneling. And one of the challenges we had is, it was the project went from 2013 to 2018, and we had some areas where we did some open cut excavation, and when you get to bigger depths and we didn't go with trenchless, that maybe some of the influence area in the cuts that would in our spec would allow for spoil backfill. We did do spoil backfill, and found out later that we had future MSC walls that kind of were over that foundation area. So we did have to come back and do some EBS to correct that, just because we were unsure with the compaction, had to do some boring. So that was one of the challenges when you have deeper cuts and projects in subsequent years. Sometimes you can do all the planning you can, but sometimes things will be missed. So that was definitely a challenge on a project of this complexity. All right, complex staging. Obviously we had to bring the old interchange up to new federal standards. So there was major profile changes. And this illustration here is a pretty good example. We had a 20-foot grade separation from the existing ramp to what the new ramp's going to be located at. So, we did a bunch of different things. In this case here, on the right-hand side, you can see some temp shoring that was installed at the top of the cut slope. There's actually a big electrical facility up there. And then on the left side, it was just laid back slopes. There's not photos of it. We used a lot of wire walls on the west leg on the interchange. We were able to maintain 5 lanes, or 3 lanes in one direction and 2 lanes in the other direction, with almost a 20-foot grade separation at with over about 1,000 feet of new pavement. But we did that with a very large temporary, we can call it a wire wall, but it actually had geogrid reinforcement contractor design. So that was successful, and that was actually in place for more than a year. Some of the bigger challenges we had, and you can kind of look at this here, with these grade separations, and especially if you had a low point in the ramp, we almost were building like a Grand Canyon. And we had storm sewer in place, but then you have the inlet protection, you got to worry about erosion. But on some of the bigger rains, we found that having inlet protection in place, even if it's non-winter conditions, it would always lead to flooding. So we had to come up with some really creative means to satisfy environmental requirements, but not flood the freeway every time it rained. And some of the slope stability, we wound up using a lot of spray on soil stabilizer, or even covering areas that weren't even topsoiled yet with EMAT and seed, and getting grass to grow in clays just to try to make this work out. So it was definitely a challenge throughout the project. Year-round construction. So major work on the interchange started in 2013 and finished in 2018. That resulted in some bottlenecks in the schedule, where some projects had to be completed by a certain point in time, or interim portions of a project just needed a tight time window just so we could maintain traffic on the freeway and move traffic around and still get the project completed. So a couple that come to mind, the Watertown Plank project, which was 2013 through 2014 project. That was one of the initial ones on the northern end of the interchange. We had to move northbound traffic onto the new northbound bridge and new northbound pavement and embankments. While that project got underway in November of 2013, And to keep schedule and keep the whole program on schedule, we need to have that completed by May of 2014. So the contractor had to essentially build 2 wraparound MSC walls, a bridge over Watertown Plank Road, and approximately 1,000 cubic yards of embankment for the new freeway from November to essentially March. Obviously, that's a terrible time period to be doing embankment. And then if anybody remembers, and I'm sure Minnesota was just as bad, the winter of 2013 and 2014, we had the polar vortex, or so they want to call it. So we had some major challenges, to keep our, we call it QMP subgrade, to get our, density or adequate compaction for density and moistures. We used a lot of fly ash on the job. That soils up there were typically wet, siltier soils. So we used a lot of fly ash, typically with a rate of we found 60 pounds per cubic yard per lift, worked out very well. So the contractor was able to utilize fly ash, which we had, as a bid item. So we didn't have to change order it, and that allowed to maintain schedule. And then the contractor on their own, that they would work for maybe a week in January, and then the cold would come in. So they would put 1 to 2 feet of sacrificial fill on top of the fly ash treated soils, and then they would dig it out and keep going. So, I mean, it was extremely challenging, but that job, finished on time, and it, using fly ash allowed us to remain on schedule. And then for winter backfill, sorry, Jason, winter backfill really quick, on our Core 1 project, we had a bridge, Blue Mountain Road, that it was demoed in October of 2014 and had to be open to traffic in May of 2015. So obviously that puts you in another bad time period. So we knew the MSC walls needed to be, built during winter months. So we actually specified a winter backfill, which was essentially a pea gravel type material that kind of took frost out of the equation, and they were allowed to build this in, temperatures in the teens and 20s. Low hazard exempt soils. This is basically exempt solid waste soils that would typically, if you had nowhere else to go with it, would have to go to a landfill. But in this case, we were allowed, with coordination with the DNR, to keep these on site. We did a lot of pre-testing to identify the soils, and, worked with the Wisconsin Department of Natural Resources to allow reuse in the right of way. The challenge we had was unknown conditions, and we found out the biggest impact was the original interchange was built in the early 60s. All the piling were wood piling that were creosote treated. So after 60, 70 years, that creosote migrated in the adjacent soils and resulted in additional impacts at a lot of locations that we didn't consider. So there was a lot of work during construction, with the DNR and the contractor to be able to find additional fill areas and keep this on site. Because to landfill it, you're talking $50 to $80 a cubic yard, versus to keep it on site, you're at $15 a cubic yard. So there's major cost impacts there. Fill factor. I'll try to hit on this pretty quick. This gets confusing. A lot of people think fill factor, expansion factor is how the material expands in the vehicle. In Wisconsin, when we're doing our earthwork balance, we expand the fills. So we take the known fill volume, the cut volume, and we expand the fill. We'd expand the known fill volume by a certain degree, assuming that the in situ soils, when you compact them to, if it's 95%, whatever type of product you're using, would actually shrink. We found out through testing, and this picture shows some deeper cuts, that in fact, it's more of a 1-to-1 ratio than what we had a plan estimated, factor 1.2. And in the past projects, we were wondering why there's always this extra dirt. So just a quick example, we had a project with 1 million yards of cut with 830,000 yards of fill using that 1.2 factor. We were thinking it was balanced, but in reality, using the 1-to-1, you got an additional 170,000 yards or so of waste that you didn't account for. And then utilization of 3D modeling, Jason really kind of hit on this too, was used a lot during design, but we did carry this into construction. We had full-time CAD tech on staff for construction delivery that allowed us to resolve a bunch of issues. And then real quick, this is plan core grading. You can kind of see that green area in the middle with the slope. This is utilizing 3D modeling from the plan section. Now, if we go to the revised core grading, this red area, basically what we did is we eliminated some plan cuts there and we added some fills. We utilized the model to confirm that the aesthetics were good with it. We analyzed the stormwater impacts, we were fine, but what this let us do was it was mutually beneficial and improved the aesthetics. It helped the contractor get rid of some excess waste kind of related to the fill factor. And there was an old northbound abutment kind of related in there that the plans would have had us cut material out, and we would have got into that material around the old timber piles. So we were able to just leave those in place. So this was definitely a win-win for both us and the contractor. Lastly, North Lake, that's the project that's happening right now that I'm the project manager on. A lot of aspects up there that we're dealing with, and all the soils are silt, and we could talk about that for a long time. But one of our biggest challenges, we have a railroad structure. We're calling this the Thames shoe fly. And because we're not on a curve, we're not able to just build a new bridge. We actually have to build a temporary bridge, put train traffic on it, and then build the permanent bridge and put trains back on the permanent structure. So that's why this project's 3 years instead of 2. One of the interesting or challenging aspects of the shoe fly structure is the timber lagging supports around the 2 abutments that you can see. The lagging, the picture doesn't do it justice. It's massive what the railroad requires. But one of the challenging parts is it's so close to the existing tracks that we're not able to dig into the existing embankment. So the lagging the piles are installed, the laggings drop down to touch existing grade, but then next year, when we build the new structure and build the wraparound secant walls, we're going to have to excavate down another 6 to 8 feet. And we're going to actually have to do that and install lagging while train traffic is on the structure, is above the area that it's being supported. So we haven't got there yet, but that's definitely a unique thing that's going to be challenging. And the reason they had to do it that way is the approval process with the railroad. If we had to install shoring, it would be in the type A influence zone, and the shoring would have required tiebacks, and it was unsure that the railroad would allow us to leave those in place. So we had to go this route. And obviously it's so narrow because you can see there's a big hotel very close to the tracks that makes this shoe fly that have to stay so close. So there's actually we had to build a retaining wall to support a retaining wall there as well. So a lot of challenges with this project, and we're hoping for a successful outcome.